Lana invited us to her house. And I think if you grew up outside the United States, like me, you appreciate that. And she served us martini and Rossi vermouth. Lana?
Thanks, Abel, for the very nice introduction and all these embarrassing stories, but please trust me, I do know now what martini is. So for those who were not present, so today's lecture will actually ultimately, hopefully, give some explanation and some ideas for the proof from what was described yesterday, but I understand there are some people who were not present, and in large part it is actually kind of independent. And let me give a quick motivation for one interesting part of today's lecture that is not entirely related to yesterday's one. So this is the ergodic theorem. Everyone knows that, I assume. And I like to call it additive ergodic theorem because there is also a multiplicative ergodic theorem, which is technically due to Furstenberg-Kesten, who proved it earlier, but it is nice to see it as a corollary of Kingman's subadditive ergodic theorem. So, and this will be something that will play a role in today's talk, so let us concentrate a little more on it. So suppose we have an ergodic dynamical system and a matrix-valued measurable function with integrable log of the norm. And then necessarily, for mu almost every omega in the phase space, there exists this limit that is called the Lyapunov exponent. It's also equal to limit of integrals of logs of such product along the trajectory, matrix products along the trajectory of the dynamical system. You see, it's multiplicative. So if n is equal to 1, then it is a direct corollary, it's a direct corollary of the additive ergodic theorem, because this condition simply becomes, so for log of the norm is a measurable function, and this condition simply becomes that this function is integrable. So, but it's a much deeper, it's an interesting statement. Specifically, so this multiplicative structure, you still have this limit, this ergodic theorem. And now let us look at something else. And we all have studied complex analysis, and we all know Jensen's formula, right? And I'd like to write it in a slightly non-standard form. So suppose we have a holomorphic function and Z1, Zni is zeros in the interior of the disk of radius r. And let us talk about counted with multiplicities. And let's take a radius epsilon less than log r. This is how I like to set it up. And let us consider this logarithmic integral, which is integral of the log of the absolute value of our function over the circle of radius e to the epsilon over 2 pi. And then I claim that your familiar Jensen's formula that everybody knows can be rewritten in such a form that this logarithmic integral, I epsilon, is equal to I0 minus the sum of the logs of absolute values. Oh, sorry, AI and Zi are the same. AI are just equal to Zi, these are the zeros. Logarithm of absolute values of the zeros between 0 and epsilon, the logarithm should be between 0 and epsilon, plus epsilon times the number of those and zeros counting multiplicities. So it's just a somewhat unfamiliar rewriting of the familiar Jensen's formula. So everyone knows this one. And what I'd like, if you haven't seen anything that I talked about yesterday, some motivation for a part of today's talk is there a multiplicative, or one can also say non-commutative analog, and a multiplicative version of Jensen's formula, like there is a multiplicative version of ergodic theorem. And so that's something that we will partially develop. And to start with this, let us actually introduce our objects a little more formally. So again, this Lyapunov exponent that I introduced, this context of Kingman's ergodic theorem, are best understood if one starts talking about special class of dynamical systems called linear cocycles. So what are linear cocycles? Again, like in this Kingman's ergodic theorem, we have an ergodic dynamical system and a matrix-valued function with integrable log, just the same premises, multiplicative ergodic theorem. And linear cocycle is a skew product that maps the point in the phase space, and this 2 should be n, sorry about that, 2 is equal to n, in the phase space multiplied by vector space Cn into itself. A point in the phase space is mapped according to our ergodic dynamics, and the vector is mapped into A of omega v, where A is our function. So iteration of this map produces precisely the matrix product that you have seen in the multiplicative ergodic theorem in the second component. And in particular, to connect with what we talked about yesterday, if T is an ergodic shift of the torus, so in shift by an incommensurate vector, these are called quasi-periodic cocycles. So an important case that will link to yesterday's talk is Schrödinger cocycles. So again, we can define potentials by, suppose we have some real valued function, and then we can define potentials, discrete potentials, by just taking values of f along the trajectory of the initial point. And we can define a family of Schrödinger operators indexed by this omega in the phase space omega with such potentials. And it turns out that it is very fruitful to consider these operators as a family from the point of view of spectral theory, in particular the spectrum, something that I defined yesterday, is almost everywhere independent of omega. And many other properties also are collective properties of the family. So these are so-called discrete Schrödinger operators, and it turns out that general theory tells us that the spectrum consists of those energies, we say, in R, such that solutions of the corresponding difference equations display certain behavior. So basically, spectrum can be defined through the properties of solutions. And these solutions can in turn be described in terms of transfer matrices. So this second difference equation can be rewritten just like this. Un plus 1 is equal to E minus V un minus un minus 1, and un is un. So we can just rewrite this second difference as this matrix form. And then iterating it, we see that un plus 1 un is related to u1 u0 through a product, through this product that we talked about, through this nth iteration of this so-called Schrödinger cocycle. So it turns out that actually there is a very neat dynamical description of the spectrum. It's called so-called Johnson's theorem for this one-dimensional difference operators, that energy is not in the spectrum if and only if the cocycle is so-called uniformly hyperbolic. I will say a little later what that means. I don't want to stop on that now. So, in particular, energies in the spectrum and Lyapunov exponent is positive, which is possible, if and only if the cocycle is non-uniformly hyperbolic. And this is usually a very interesting behavior from the point of view of dynamical systems. So in this sense, to study the spectrum is the property of this one-parameter family, is a set defined for this one-parameter family of the cocycle, and it can be viewed as a bifurcation set for this family. So another nice general fact is that absolutely continuous spectrum, again, I don't want to define what it is, but it can be fully expressed through the behavior of Lyapunov exponent. So again, we define Lyapunov exponent of the cocycle, but once everything is fixed, we can just say it's a function of energy. And absolutely continuous spectrum is a closure of the set of essential closure of the set of zero Lyapunov exponents. So in general, Schrödinger cocycles are probably the simplest classes of dynamical systems that are compatible with both KM phenomena. This is something that I will talk about tomorrow, and non-uniform hyperbolicity. So these are two both very interesting phenomena in dynamical systems, and this plays out very nicely for Schrödinger cocycles. Okay, so back to our multiplicative ergodic theorem. Given a cocycle, we have Lyapunov exponent, well defined, and this limit holds for almost every omega. Now, if cocycle is d-dimensional, so this is n-dimensional, so then actually by considering outer products, one can define multiple Lyapunov exponents. So one can define Lyapunov exponents Lk, just taking the limits of such integrals. An is the nth iteration of the cocycle, and sigma k is the k singular value of this matrix. So it's easy to see from this theorem that such limits do exist, and they're called Lyapunov exponents of higher dimensional cocycles. So we note that if the cocycle is symplectic, and in particular Schrödinger cocycles are always symplectic, then Lyapunov exponents come in pairs, so positive and negative. And so if the cocycle is symplectic to d-dimensional cocycles, there will be d positive Lyapunov exponents, d non-negative Lyapunov exponents, and d non-positive ones. That they're opposites. Okay. So now going back to quasi-periodic cocycles, and let's assume that our cocycle is quasi-periodic and our function f is analytic. These are and then if it is analytic, it's very fruitful to complexify it. This was actually first done by Michel Herman to produce the first nice example of non-uniform hyperbolicity, when he proved that Lyapunov exponents are always bigger than log lambda for the almost Mathieu operators that we discussed yesterday. But so almost Mathieu operator leads to a cocycle where this f is specifically 2 lambda cosine of theta. Okay, so now, but let us look at a complexified Lyapunov exponent, which is simply, instead of theta, we plug in theta plus I epsilon. So we go out in a complex plane. And Avila, in his global theory of analytic cocycles, started a systematic study of this complexified Lyapunov exponents as function of epsilon. And it is not difficult to see that it is actually, it's a convex function. It's a corollary of the Hadamard three-circle theorem. And therefore, there is a well-defined acceleration, the derivative at 0 of this function. And one nice discovery of Avila, it's kind of the beginning of his, the foundation of his global theory, is that this acceleration is quantized. So namely, this function L epsilon as a function of epsilon behaves this way, okay, like a tropical polynomial. So there are some turning points, epsilon 1, epsilon 2, etc. And the slopes are necessarily integers, growing integer slopes, k1, k2. So it has been completely unclear so there are these kind of mysterious turning points and integer slopes associated with each of these simple objects, this cocycle. And it was a little bit of a mystery. What are they? What is their significance, and how are they determined? And we just, Avila's theory just tells us that they exist. Okay, so in particular, for the almost Mathieu operator, when this function f is equal to 2 lambda cosine, this picture allows 3 different regimes. So this is a regime where lambda less than 1, lambda bigger than 1, and lambda equal to 1. So this acceleration, this Lyapunov exponent is 0 in an interval and then becomes 1. Then it is for this critical value, lambda equal to 1. This is the graph, and this is the graph for lambda bigger than 1. Now, so as we discussed, the classical Ten-Martini problem was proved for the almost Mathieu operator, and there has been this big open problem to prove it, at least for perturbations of it. But let us look at the perturbations of the almost Mathieu operator from this point of view. How does this picture change? And we see that these are typical analytic perturbations. So here we see that this is what can happen. So here this acceleration that was 1 can become 0. Here acceleration would stay 0. But basically this property acceleration, so it is 0, 1, and 1 in this picture. But we see that it is unstable. It is, does not survive even small analytic perturbation. And so let me first, before I go back to my promised multiplicative Jensen's formula that I hope you are wondering what that is, let me actually answer the question from yesterday, because I promised to, I formulated a theorem that the Ten-Martini problem holds for an open analytic set of operators, and now I will be able to define it. So let us define the generalized acceleration, which is the acceleration, the derivative at the first turning point. So you see that for the almost Mathieu operator, it will be 1 in this case, 1 in this case, the turning point is right at 0, and 1 also in this case. So it is always 1. And we see that for analytic perturbations, it is also always 1. So because this, for example, this picture is the most problematic, acceleration can drop from around 1 to 0. But after the first turning point, it's still necessarily 1. So, and this is actually a motivation. And we say that operator is of type 1 if it has this generalized acceleration equal to 1 everywhere on the spectrum. And the nice property of it is that the generalized acceleration is stable. So once it is true for an operator, it's true for its analytic neighborhood. And so in particular, operators of type 1 include all these open sets around some popular models. Okay, so now I'm ready to answer the question from yesterday, and the 10-Martini problem, that is the fact that the spectrum is a Cantor set for all irrational alpha, holds for all operators of type 1. So it's not true for rational. For rational, it's always a finite union of intervals, but for all irrational, the spectrum is necessarily a Cantor set. So I'll just note that, repeat what I said yesterday, that prior to this theorem, there were no such results for analytic V other than the lambda cosine. Okay, so again, why type 1 and what is its significance? And now we are ready to almost understand it. So again, let me go back to Jensen's formula. I already showed it. And let us graph this function I epsilon as a function of epsilon. So this means, this is Jensen's formula, and this means precisely that at each logarithm, oh my God, yeah, now it is z again. So a is z, a is z. So at each logarithm of absolute value of 0, we do have a turning point, right, because of this term. And the slopes are actually equal to, actually because of this term, but slopes are equal to the cumulative multiplicity, the total number of zeros up to this level. So this is just an illustration. This is just a graph of this function. This is an illustration of Jensen's formula. So does this graph look familiar? Well, yeah, we just saw it in this global theory, right? Except for here, we didn't know what these turning points and what these slopes were. And here we do in Jensen's formula. So this suggests that there is some sort of a connection. And indeed, you see, of course, everyone should realize by now that Jensen's formula is just a statement about Lyapunov exponent of one-dimensional cocycles, right? Because what is one-dimensional cocycle? It is just, you have x and v. V is a number now. X is a one-dimensional analytic quasi-periodic cocycle, one frequency, right? X is a number on the circle. V is a complex number. And it is, this pair is mapped into x plus alpha. And f of x, where f is your analytic function, times the number v. So that logarithmic integral that we wrote in the Jensen's formula, of course, it is just equal. You don't even need the limit, right? It is so it is equal to this, right? Because once you do a shift, you don't, because it is additive, right? Logarithm of this product is the sum of the logarithm, right? And integral of each logarithm is the same because you just do the shift. So, and this limit is, of course, equal to, by what we just discussed, the Lyapunov exponent of this one-dimensional cocycle. So Jensen's formula actually is a dynamical statement. It's a statement about Lyapunov exponents of one-dimensional cocycles. So the question is now again, but with a little more hope, is there a multiplicative version? So it would be natural for this formula then to hold for high-dimensional cocycles as well, right? But it wouldn't be so clear what this, so these are just logarithms of the zeros of this function f, and what is their dynamical meaning, right? And indeed, so that's what I want to talk about now. There is a multiplicative version. So specifically for quasi-periodic Schrödinger cocycles, we do have this, what we call multiplicative Jensen's formula. And of course, if you don't specify what these Li hat are, this will not say much new, will not give you much new information compared to Avila's global theory. That's precisely its statement. But we do specify what they are, and it's very exciting. So they are so-called dual Lyapunov exponents. So, and these are my co-authors, Ling Ruige, Jiangung Yu, and Chizhu. So, so let me explain what these dual Lyapunov exponents are. So, but once I do, this kind of demystifies this global theory, because this means that these turning points are precisely these dual Lyapunov exponents, and these integer slopes are precisely their cumulative multiplicities, cumulative numbers up to this level. Okay, so to describe dual Lyapunov exponents, I need to introduce yet another concept called Aubry duality. So again, this will be more understandable for those present at yesterday's lecture. Remember when I introduced the magnetic field, I said that basically introducing a magnetic field is just like introducing a gauge field A and B, such that when you go counterclockwise around each cell, you incorporate 2 pi alpha. So, and any gauge field will lead to a unitarily equivalent operator. And so we introduced a specific gauge field yesterday where B's were e to the 2 pi I m alpha, and A's were just 1, right? But if we just rotate it 90 degrees, so if we have A, have weights, and B, B 1, so pi over 2 rotation of the gauge field, this, as I mentioned yesterday, leads to a unitarily equivalent operator. And formally, this unitary equivalence is actually quite neat. So it, again, this is very easy to see that it's a unitary equivalence of two-dimensional operators, but again, as mentioned yesterday, this two-dimensional operator itself is unitarily equivalent to a direct integral of one-dimensional operators, and that brings us to this space. And here is a unitary mapping L2 of S1 times Z, so corresponding to this direct integral space into itself, which is a Fourier transform in both variables. It takes continuous variables into discrete and discrete into continuous with such a shift. So, and this is a transformation that precisely corresponds to just 90-degree rotation of the gauge field. It's a computation. So this is a unitary transformation of a two-dimensional operator, but it transforms corresponding one-dimensional operator into something different. In particular, how does it act? So if you start with an operator family of this form, with function V here, the dual family you take Fourier transform in both variables, right? So for the dual family, you have a Toeplitz operator, fixed Toeplitz operator instead of the Laplacian, with coefficients given by Fourier coefficients of the function v. And the discrete Laplacian is mapped into the potential given by twice cosine. And that's why this almost mature operator is special, because it's a self-dual family. If V itself is a lambda cosine, so here you get a discrete Laplacian, and after renormalization, you get just another operator with lambda 1 cosine with a different lambda. So, however, for general V, you will have that. All right. And if V is a trigonometric polynomial, like this, from minus d to d, then it becomes a finite difference equation, 2D difference equation. And it similarly leads to a cocycle, right? The equation h psi equal to e psi leads to a cocycle, just it will be not a SL2C cocycles, it will be a symplectic 2D-dimensional cocycle. And as we discussed, being a cocycle, it has Lyapunov exponents. It's still a quasi-periodic cocycle. One can write it down explicitly. And it has Lyapunov exponents, and it has multiple Lyapunov exponents. It has d non-negative Lyapunov exponents, and the other are minus those. And let us denote by LD hat, L1 hat, it's d non-negative Lyapunov exponents. And these are precisely what we call the dual Lyapunov exponents. So they are non-negative exponents of this dual cocycle. Now, what I sweep under the rug here a little bit is that if V is not a trig polynomial, if V is a true analytic function, so we don't have a cocycle here, we have an infinite range operator, right? So what do we do then? In this case, we take cutoffs, finite cutoffs of function V, and for each we compute this top Lyapunov exponents starting from, so 1 is the smallest one and so forth. And it turns out that they stabilize. It's a part of the theorem that as the cutoff d goes to infinity, these Lyapunov exponents converge to some numbers, and this is what we call dual Lyapunov exponents in case of analytic. Okay, so in particular, this leads to a neat spectral explanation of the classical Jensen's formula. So now you already realize that it's a dynamical statement. It's a statement about Lyapunov exponents of one-dimensional cocycle. But it's actually also a spectral statement, because again, this is our formula for the behavior of Lyapunov exponent. But let's consider a very simple operator, quasi-periodic, but without the Laplacian part. So operator depends on x, and it multiplies vector u n in n's coordinate by v of x plus n alpha. So just the potential. Then its dual, according to what we discussed, is just the constant Toeplitz operator. So no quasi-periodicity. So it is just one matrix. And it's Lyapunov, so it's a constant symplectic cocycle, and leads to constant symplectic cocycles, and one can compute its Lyapunov exponents, and it turns out that they are precisely up to 2 pi logarithms of absolute values of zeros of the function v. And so this is therefore kind of a spectral version of the Jensen's theorem. Okay, so I'll now go back soon to my type 1 operators, but before that I'm tempted to give So this theorem actually has lots of various corollaries. This or 10 Martini proof is just one of those, but let us recall, we already mentioned the theorem of Johnson, that spectrum of such second difference operator is the set of E such that Lyapunov exponent is 0. Either Lyapunov exponent is 0 or the transfer matrix cocycle is non-uniformly hyperbolic. So this is a nice description, but of course it's hard to check whether it's non-uniformly hyperbolic or not. It's kind of a very non-explicit description. And so a corollary of this multiplicative Jensen's formula, one corollary is that actually one has a much neater description of the spectrum for operators with, for analytic quasi-periodic operators. The spectrum is just the set of energies where either the Lyapunov exponent is 0 or the first dual Lyapunov exponent is 0. It's a purely analytic kind of description of the spectrum. Okay, so what makes operators of type 1 particularly special? And why, what is the relation with this dual Lyapunov exponent? It turns out that operators of type 1s are precisely operators whose kind of dual cocycle. So as we discussed, one can, let us just concentrate on the trig polynomial case. Again, there are some subtleties in going to analytic, but let's assume we are in the trig polynomial case. So the dual this symplectic 2D dimensional cocycle for V being a trig polynomial is called the dual cocycle. So dual cocycle may be very, very large. D can be large. So it turns out that these operators of type 1 are precisely the operators whose dual cocycle is partially hyperbolic with two-dimensional center. And this is actually, if you think about it, it's a pretty easy corollary of this multiplicative Jensen's formula. So what do I mean by that? What is this? So what is this? What does it mean partially hyperbolic with two-dimensional center? Again, the cocycle kind of acts on pairs x C2D, right? But it follows that there is a decomposition for each phase theta. There is a decomposition of this C2D into this center space, stable space, and unstable space, right? Such that whenever we start in the unstable space, we get, so this is for the dual cocycle. So we have this uniform exponential growth, and whenever we start in the unstable space for and going to plus infinity, we have uniform exponential decay. So, and in center there is basically okay, it emits this. So in center you have neither growth nor decay. Okay, so how does it play out and why is it important? So there are two very important ingredients that I want to discuss. So one is the following. So there is so I mentioned that there is a very nice Kotani theory that characterizes absolutely continuous spectrum as a set for just two-dimensional cocycles, as a set, as the essential closure of the set where Lyapunov exponent is 0. So there was an attempt at, and basically the reason why it is absolutely continuous spectrum, because once Lyapunov exponent is 0, there is so-called L2 reducibility. So that means that coordinates can be changed for your cocycle by an L2 transformation that in such a way to reduce it to a rotation. So now, there was an attempt to extend this to higher dimensional cocycles by Kotani and Simon back in the 80s. And they were only able to do it in case all Lyapunov exponents are 0. And they asked a question in the paper from 87, I think. So it would be very natural to extend it to situations when some Lyapunov exponent are 0. And so we kind of make the first step towards the solution of this Kotani-Simon problem. Namely, so if the original dynamical system is minimal, and we have this situation, partial hyperbolicity with two-dimensional centers, so exactly two central Lyapunov exponents are 0, and the others are positive, and like it says here, it is not enough that they are positive, you have kind of uniform growth and uniform decay. That's what it means, that corresponding cocycles are dominated, so that you have some uniformity in the behavior outside this two-dimensional subspace. Then you have L2 reducibility in the center. And that is what is crucial for that's one crucial ingredient for our 10-Martini proof. And I want to advertise that Lynn Gruyer, here is his picture again, almost has a full result ready. So if you have just full solution of Kotani-Simon problem, it just takes more technical effort. Okay, so another important ingredient is this basically, as I mentioned yesterday, there was this nice Puget's argument that basically allowed, that was based on the fact that for second difference operators, point spectrum is necessarily simple. So indeed, it's a very simple fact for second difference operator based on the constancy of the Wronskian, but it doesn't extend to higher dimension, to higher difference operators, and therefore to higher dimensional cocycles. And this was an extremely important, very simple but extremely important ingredient in the proofs of 10-Martini problem, the original 10-Martini problem. So, and here we show that actually the property that we called essential second differenceness, that if the cocycle is partially hyperbolic with two-dimensional center, then point spectrum is also necessarily simple. So you can have like a difference equation of 100 difference equations, but as long as it is partially the cocycle is partially hyperbolic with two-dimensional center, you have exactly the same properties as the second difference equations. And this is another nice part of the argument. So, yeah, I already mention this. Okay. So another thing that I want to emphasize that is, again, about, so this is going to the proof of the 10-Martini problem, is that I spent some time explaining yesterday how the proof was a miraculous collaboration of two very different approaches, one from the Liouville side and one from the Diophantine side. And actually, this Liouville side approach, this algebraic miracle of Choi, Elliott, and Yu is something that is still, we do not have any handle on how to do it for anything other than the almost Mathieu operator. And so this was something that actually was supposed to kill any attempt at proving the result for all alpha for other families. However, here we develop an argument that actually is uniform in alpha. And I want to mention that a little more for the experts. So again, Puget's argument, based on the simplicity of eigenfunctions for the dual model, implies that it's impossible to reduce the original cocycle to the identity. But this has Diophantine abstractions, so it does not work for non-Diophantine. And what we do instead is we show that simplicity of almost localized eigenfunctions implies that it is impossible to reduce not to the identity, but to a rotation with zero rotation number. So, namely, that's what we prove as a result. That if you take a Schrödinger cocycle associated with a type 1 operator, then we cannot have an analytic coordinate change such that it reduces to a rotation with zero rotation number. And so this works uniformly for all irrational alpha. And so I will just need to wrap it up. So let me just say a few words about the strategy. So again, our strategy is different approaches in the regimes where the Lyapunov exponent of the original model is 0 and it is positive. So if it is 0, we have, for the original model, we have the Kotani theory. And then we can basically follow some arguments in our paper with Avila. But the difficulty is precisely this Diophantine abstraction. But here we invoke this absence of rotation reducibility to with zero rotation number, and this leads to a contradiction. Now, if Lyapunov exponent is positive, then we actually need to work from the start with the dual, which is long range. So we need this extension of Kotani theory for operators with partially hyperbolic cocycles. And so by the results that I mentioned, we obtain rotations reducibility for these dual finite range cocycles, and then again invoke similar arguments to show that cocycle cannot be partially analytically rotation reducible in an interval. And I will stop here. So just a little advertisement for tomorrow's talk. So the first half of the talk will be kind of independent. I will just talk about the history and some history of small denominators and some other related results. And then toward the end, I will explain again some results related to this one-frequency quasi-periodic operators where small denominators were beaten by various new strategies involving, in particular, these dual Lyapunov exponents. Thank you very much.